Alright, welcome to lesson 4.03. Here we're going to be looking at tables and graphs of radical functions and using them to answer some real-world problems. Let's get started. Alright, so the first part of the discovery problem, not something you need to copy down. Just want you to read through it and make a conclusion, answer this question based on the information you're given in the situation. Go ahead and do that now. Write out your answer in your notebook. Alright, hopefully you made a conclusion and have some good reasoning as to why you're going to arrest one of the drivers. Let's go ahead and now take it up a notch. Let's go ahead and look at some scientific data that might allow us to make our conclusion with more confidence. Right? We might say, look, I believe that this is the car driver who was speeding, but I can't be so sure. So let's try and make our conclusion more sound. Here we have an equation which actually allows us to look at the relationship between the speed of a car in miles per hour, which is S, and D, which is the length of the skid marks left by the car's tires. So here's that equation. S is equal to 15.9 times the square root of D. And here is what the graph of that function looks like. What I want you to do right now is go ahead and write out this intro and the graph and label the axes appropriately. Okay, hopefully you have these labeled correctly. It's really important, obviously, to have the axes labeled correctly. Here our input is the distance of the skid marks in meters, and the output, or the y value of each coordinate point, is the speed in miles per hour. Okay, now I'm going to go ahead and put some questions up that I want you to answer, and you don't need to write the questions down, you need to write your answer down, because in your answer you'll be repeating sort of the part of the question that you needed to answer, and so it'll be very clear the question that you're answering. Alright, here are the questions. Let's take a look at number one, just so you feel super confident using this graph to help you answer these questions. So how fast was car number one moving at the time of the crash? Well, car number one had skid marks that were 4 meters long, and I notice here that each tick mark is counting by 2, so 4 meters would be right here. And if I look up at the value of the graph, it appears to be right here. So if I am very accurate, I can actually use a little drawing here to help myself pinpoint the speed that I'm looking for. And if I notice each tick mark in the y direction is 5 miles per hour, so this appears to be just between 30 and 35, so I might say 32.5 miles per hour. Okay, so go ahead and complete these on your own, and then when you're done, press play and we'll talk about some of the more important ones. Alright, hopefully that went really well and you have some good sound answers to these questions. I want to discuss some of the ones at the end here because this is a really important concept when dealing with radical functions. What is going to happen to my output, the speed, as the skid marks, D, increase? Not too hard to see what's happening here. The longer the skid marks, or the greater the value of D, the greater the value of S, or the speed that the car was traveling. And so that's pretty easy to see. Speed will increase as D increases. But let's make our claim even more precise.
To do this, we would like to say something about the way that the speed is increasing. Is it increasing more and more as the length of our skid marks increases, or is it going to be increasing by less and less? And to do this, we can just consider two parts of the graph. Let's first look at the beginning of the graph, and let's notice how much the speed will increase if your skid marks increase from 0 meters to 10 meters. This isn't hard to do. We know that if your skid marks are 0 meters, then you are traveling at 0 miles per hour. And by looking at the graph, if your skid marks were 10 meters long, it appears that you are traveling at around 45 miles per hour. Now let's compare this to what the change in speed is if our skid marks go from 30 meters to 40 meters. Looking at the graph, skid marks of 30 meters would imply that you are traveling about 85 miles per hour. If your skid marks are 40 meters long, the graph and the model predict that you would be traveling at about, this looks to be close to 100 miles per hour, maybe a little less. So out here, when your skid marks are increasing by 10 meters, the speed only increased by maybe about 15 miles per hour. Whereas at the very beginning, when our skid marks increased by 10 meters, our speed increased by almost 40 miles per hour. So the statement that we can make is that as the skid marks increase in length, the speed will be increasing by less and less. And this is an important characteristic of radical functions. As we move farther out to the right, as the independent variable increases, the average rate of change, or the slope of our graph, is going to decrease. Notice that at the beginning of my function, if I looked at the slope and I said, well, how steep is it? You might say, this is pretty steep. And relatively, as I move out here, the slope is getting more shallow. And of course, slope and average rate of change, same idea. And so that allows us to make a really nice, strong claim about the average rate of change of radical functions. And we'll go ahead and do that now. So as I mentioned, a couple of really key points that we want to get down here. The first couple should be pretty straightforward. When dealing with real-world problems, we want to identify a couple of important things. What are the inputs, or independent variables, and what is the output, or dependent variable? What's the information we're given? Obviously, we want to make sure we incorporate that into our answers, our solutions. And then also we want to identify what we're trying to find. That will allow us to answer questions accurately and efficiently. Always, always, always make sure that your information that you're given goes into the answer that you write. And what I mean by that is your answer should be written in context, right? You shouldn't just throw out a number without explaining what it means in terms of the situation, right? In the previous situation that we saw, you'd want to make sure that you include whether you're talking about a skid mark or a speed and what the units are. And last, but certainly not least, what we just spoke about, which is that the rate of change of a radical function decreases over the domain of the function. What we saw is that as the skid marks increased in length, the speed did increase, but it increased by less and less. And that's what this statement is saying here. So maybe take a second, go back to the previous slide, and really make sure that this statement here makes sense. When you're done, let's go ahead and try one more problem. All right, so here's what I want you to spend a few minutes doing. When we looked at the graph of our function for speed in terms of skid mark length, we were able to clearly see that their rate of change is decreasing. And what I want you to do is spend a couple minutes proving that to yourself using the equation now. And I gave you a little outline for how you might do that when we discussed looking at the rate of change in the discovery problem. And it might be helpful to also look back at your notes on average rate of change and how to find that. But you should have some work shown and a little bit of an explanation for your work come Monday. We'll take a look at that together.